from SISSA in Trieste, and then he was postdoc at the University of Manchester. He also worked in a group of theory condensed matter of the University of Cambridge. And after these experiences, he has been lecturer at the National Institute of Condensed Matter and leading researcher at the National Research Council, CNR. So from 2012 to 2020, he has been professor of physics at IMT of Lucca, and his research activities span from network sciences in finance to fake news modeling on networks. And it is a real honor to have Guido with us. And now I leave the stage to you, Guido. Thank you.
Okay, now the honor is mine. Thank you. Thank you for the introduction. I put many slides, so I'll be very fast today, but please stop me if I'm too fast. But essentially, there are 2 points that I would like to convey today. And is that, okay, we're doing an activity on the detection, measurement of information disorder, more than detection. And the second message on this activity that I'm going to present is that we do that through the network analysis. So I'm going to spend a little bit of time in explaining in detail what is our network framework that we used in order to achieve such results. And allow me to be pretty fast on that. And okay, now it works. So the idea is that networks is one of the instruments that we have in order to quantify phenomena that we determine as complex phenomena. And this could be behavior of crowd, of which this misinformation and disorder of information is one particularly interesting topic. The brain, the internet, whenever we have plenty of things going together, then there is some sort of unexpected quoted behavior that emerges out of this interaction. And I mean, of course, we don't believe in authority principle, but there are a few, how to say, suggestions that are telling us, and I mean, I would say educated answers, that this is really the complexity age. Now, Hawking, for example, studied, we all know, I mean, the theoretical physics, but also pointed out that we understood many of the things that are describing the constituent of matter, the constituent of light, energy, the interaction between the two. And now it's the time to apply this law and see something else. It's a little bit, this is not his words or mine. So I mean, let's put Hawking on the side, let's go below. And what is my opinion is like in a situation where you know how to build bricks, you know how to use steel, you know how to use iron, glass, and then these things you know, and then you have to start building buildings. So it's architecture. So once you know the bricks, the steel, and the stuff, you can do different buildings. You can do churches, you can do places where you live, offices, and you can do in different shapes. So how the elementary things combine and give the shapes that we see around, this is a little bit in Hawking idea what is complexity. We know about Giorgio, it got a Nobel Prize. Of course, nothing to do with Giorgio, so let's put this clear, but the Nobel has been given to him for the studies on frustration, on how for example, disorder can be determined. So there is a good series of, how to say, clues that physics could play a role in describing what we have around us. And what do we have around us? So what is the data explanation behind these clues that we are really living the complexity age? Is the data deluge, is called in such a way. So the fact that the number of information that is available to everybody is growing constantly and is already huge. If you think about all we know and you transform in bits, so information, and historical facts. I mean, from the first paintings on a cave to the latest book. Okay, this is a certain amount of information. Okay, this amount of information is doubled in less than 1 year. So it's growing exponentially. It's a multiplicative process. So every year or fraction of year, we double that. Of course, not all the information has the same value. I mean, the books by Homer and what we bought on Amazon have not the same level of importance for mankind. But the point is that we have all this information available, and there is some signal out of the noise. If you look at the number of this bit that we are producing, you see this is estimate. Nobody really knows what's going on now at the moment, but it's the estimate that you see there is 1.7 megabytes per second. The latest I could find on the internet. You do an exercise and go on Google and look by yourself. So megabyte means 10 to the 6 per second means that we have 10 to the 5 seconds per day. So we have 11, and then this is 1 day, then you put another 3, and then you're right to 14, 15. And so this is per person. Add 10 to the 9, because we have 10 to the 9 person in the world. Of course, nobody is producing information at the same rate, but even if it's 10 to the 8, 10 to the 7, there is a drastic reduction. We're talking about Avogadro numbers. Whatever you would like to go around and takes directly the estimate in the world per year, or whatever is the recent estimation, and you compute per person, per second, and you transform in the planet and per year, we are about 10 to the 20. Okay, this is a very conservative estimate. So we know already how to deal with these numbers, and this is why statistical physics could be useful, why we got interested. And we got a bunch of guys that 2 centuries ago, 1 century and a half, dealt with such a problem of Avogadro number and extracting information out of that. And this we have when we consider a simple bottle of water. And in this bottle of water, there is 10 times 10 moles, order of 10 moles of water. And then you have scatterings of particles inside. Of course, particles of water are simple objects, even if they are many. Still, they can, in their interaction, produce something completely unexpected. So these guys studied what was going on. They found that, okay, these are scatterings, so we only need to know their velocity, okay, into the material of these particles of water. That the distribution of their velocities is peaked around a certain value. And if you make the right assumption and you say, okay, I'm not interested anymore in knowing exactly what's going on, scattering by scattering, it will be impossible to follow. I just reduce my expectation to what's going on average. This distribution of velocity are very well peaked around the mean value. I use this mean value, and then I discover something. What I discover, that I can put into the relation what's going on at the microscopic scale, at the scale of the molecule, with what's going on at the macroscopic scale myself. So I can measure pressure, can measure the volume, I can measure temperature. And these are in relation with the average square velocity of these particles. Okay, so this is the idea. So the idea is that when I move to the modern society, I would like to apply similar laws and extract from individual behavior what could be the behavior of a crowd. This is the idea, more or less like Psycho story, if you have read Asimov. Well, there are various problems. The most important is that nobody in our community is either Maxwell or Boltzmann or Gibbs. I mean, so this is the first big problem. Second big problem is that we are more complicated, not complex, than a particle of water. So not only velocity is good for us to determine what we're doing. So we need much more parameters. On top of that, those parameters very often are not distributed according to a very well-behaving statistical distribution. Rather, they are long tail, if not directly power laws. So, you know, the meaning of the average quantity is ill-defined. Sometimes fluctuations are so wide that, you know, any value can be okay. I mean, so average really means nothing. So we lack at the moment, which is the connection for all these reasons, which is the connection between individual behavior and the macroscopic behavior of crowds. So how a country will react to misinformation, for example. So this is the idea. On the other hand, I mean, this is the path. Many people are following that. We'll see how this is achieved, what we have achieved, and why the people went in this direction. So I hope that for the moment I'm justified to continue in this talk. I mean, so this is the idea as a physicist we have in mind. If general laws, statistically based, can explain to us which is the dynamics, which is the evolution of a system, an object. The properties of this system, of course, must be a complex system, so composed by many parts. All we know about these systems is that they interact a lot, and this interaction creates the new behavior. Now, the geometry of the interaction, I know now, and this is network. So network is the mathematics, in some sense, of this kind of complexity. And this is also why, I mean, a little bit of advertisement, this is also why we are firmly convinced that physics can be applied to social sciences. So I just suggest to have a look to this paper we published some years ago. And even if you disagree, I mean, I would like to see why. The point is that differently from other systems, we're not considering things that are happening on a lattice, that is a way to describe, you know, the three-dimensional space, the real space around us, but we are considering phenomena that happens on a stranger structure that resembles a lattice, but is not a lattice, it's a network. And the network is any set composed by vertices and their connections. These connections we call edges, as mathematicians do, or links, as we physicists do. I mean, I actually use more edges than links. Can be of different kind. For the moment, well, for this talk, but for many applications, we essentially need only two kinds of edges, the one that are directed and the one who are not. What does it mean, a correlation made by an undirected edge? Okay, for example, A and D, A can go to D, D can go to A can exchange information with D can exchange information with A. They are connected in some sense. They can, you know, exchange emails, for example. But whenever I send one single email, whenever I do a phone call, well, that's different. Then there is one that is calling and one that is receiving. So A is calling B, for example. And so these are the directed graphs. In the first case, we have some social phenomena, and in the second case, we have other social phenomena. If we exchange message on Twitter, okay, we are on this kind. If I retweet a tweet that you are just publishing, well, this is, there is a direction. So it's me taking your tweet and retweeting around. So the two cases are important, but just want to mention these things. Very, very fast, but probably you are an expert of networks, so I'm wasting your time. Eventually even my time, I don't know, but let me be fast on that, so no problem. networks of this kind have one very particular, a set of very particular properties. I will be very fast in that. Some quantities, most notably the degree, so the number of connection per vertex, have a very fat tail. Many cases are, well, let's say very heterogeneous, so this degree can vary a lot. Technically, is power law distributed. Those networks are small world structures. You can travel them very easily in few steps. They're also very clusterized. They're not uniform in how the degrees are distributed within the object. We already said that, but this is a bit more. So the most clusterized objects are nearby, are connected one with the other. And of course, as a result, some vertices are more important than others. What does it mean that in practice? I mean, much more, of course, scale invariance. If you consider, I mean, if you stop here and we ask everybody and we divide the males and females, with how much you're tall, okay? And so we plot how many people have a certain height and will be, 180 meters, 180 centimeters, 1.80 meters. That would be average, 1.70 something, whatever. Okay, there will be some people shorter, some people taller, but I mean, there will be less than the average. And in principle, they would be, 20 centimeters less at most, no more than that. I mean, this tail goes down very fast. But when I ask, are we on Facebook and by chance there is a football player in this audience today? Okay, I can have, 100 friends on Facebook. This guy can have 10 to the 5. Okay, this is a huge variation in that network of friendship that we don't experience. We don't have experience of that in our Gaussian life, let's say. We are used to see these bell-shaped curves. It's like, checking how much you're tall today in this audience and find that some people is, 2 millimeters tall and some other 300 meters. That would be strange, no? Okay, so this is the first thing that happens in networks, that we are dealing with strange stuff. And this is true. I mean, this has been questioned recently. We took the same database, we remade the analysis. I mean, that's true. It's truly scale-free. I mean, still to now, I mean, this has been undisputed what we found. So any deviation can be just explained with the fact that we're doing finite size analysis. And if you don't do that properly, then you can find deviation. But if you do that properly, there's no question. I mean, we have to talk about that. Small world is something we learned from sociologists. If you want to know which is the structure of society, and Milgram made it in Americas in the 67, and how many steps are needed to take one random guy from the telephone list and connect this random guy with a target person that is a friend nearby, living, working in the bank where I live, then on average 6 steps are enough. So this is what the 6 degrees of separation. But this was 55 years ago. Now it's pretty different. If you are on Facebook, no way that you need the 6 degrees of separation, much less. I mean, the people in Milan, Sebastiano Vigna, Paolo Boldi, and co-workers worked on Facebook data, and they found that the mean value is less than 4, 3.5. The model of this distribution is even less, so it's 3.4. So few steps are enough to travel all the people that have an account on Facebook. So that's particularly impressive. Communities. These networks are clusterized. This is important for what we're going to see about the news in a while. How can I make a sense of that? Well, in all social networks, the communities arise because the structure is that of a bipartite network. What is a bipartite network? It's a network that is composed by 2 classes of vertices, the yellow circled, the green squared, for example. And the green could be, for example, movie, okay? And the yellow can be actors. So 1, 2, and 3 played in the same movie, A, but 2 also played in another movie, B, with 5, and so on and so forth. So when you build this structure, which you have actors, actresses, anybody, people on the left, and you have movies on the right, then you can connect people if they played in the same movie. You can connect the movies if at least one person is playing in both. And then you have the projection on the yellow layer and the projection on the green layer. And in this particular case, the projection that you have on the left is this one. And 1, 2, and 3, you see, they form a very connected structure. This is a complete subgraph, it's called. And 2 is also connected with 5. That is another complete subgraph because together with 6 and 7 played in D. So they are joined by this fact, and so on for the green part. So once you represent everything as a bipartite network and you do the projection, almost automatically you find this community. So almost automatically you find that there are subparts that are more densely connected. When you study the centrality, so how much one vertex is important with respect to the other, these two concepts of community and centrality join together in some sense. So there are various measures of centrality, which is more important in a network. It can be the one who has more connection. It can be the one who travels less to visit all the others. It can be the guy who's sitting in between and everybody has to pass through it to visit all the others. It can be something more complicated, that is eigenvector centrality. We don't need today, but point is that the centrality measurements are pretty different one from the other. This is a great picture taken from Wikipedia. It's the same graph, but we vary the definition of centrality we are interested in, and we color with this heat map in red, which is most central, and in blue, which is less central. And you see, according to the definition, it can be this the most central guy, it can be this the most central guy, these could be the most central guys, or these can be the most central guys. Okay, and there are explanations why it is so for all this definition. The point is that once you have a measure of centrality that you believe is appropriate for what you're considering, then you can also find the communities, and this is how clustering is done with the Newman-Girvan algorithm and so on and so forth. Let's travel fast towards fake news. This is something that always was around. I mean, this is time invariant behavior. In the past, this is a plot made from Renaissance Florentine families, vertices, and an edge means an alliance. Alliance, how you measure? If two members of the two families organized a marriage, one with the other, so the weddings between all these families. This means an alliance at the time. So no love stories, unfortunately, I'm afraid, at the time. So who is most central here? Well, there are various definitions, but certainly Medici seems to be well posed, well positioned in this. No? Who's not? Well, the guys who are isolated or the dangling bonds. I mean, these light yellow guys here. So if these, you see this plot and you're asked, according to you, who has the power in the city? Well, Medici is educated ansatz, I would say. And if somebody, would like to take the power because it's at the periphery of the power, where do you expect trouble? Well, Pazzi is an educated ansatz. No? So this, you don't need to know story. You simply have to follow the fictions on Rai Uno or Rai or whatever. So if you see the Medici fiction, you know about Congiure de Pazzi. So they try to kill everybody and gain the power there. Not with marriages, not with weddings. Point is that not only in Medici time, this is what happens, but also now is what happens. If you take the data from a telephone call by a company who gave a tiny part of one day of their data, then you see again that you have more central vertices and stars around those guys. And you see over and over in this structure. So the point is, okay, let's go studying fake news on a social network. Take in mind that we can represent the network. Take in mind that this network is not uniform, like a net of fishermen. Okay, you have one vertex and then one vertex up, one down, one on the left, one on the right. And then this regular structure is repeated over and over. Not at all. This is the geometry. And this is very robust. This happens always. Okay, so this is important because otherwise things cannot be understood very well. So what people is trying to do to get what's going on in a community once you know what the individual are doing. So we were in Florence, remain in Florence, so they use Paolo and Francesca names from the comedy by Dante. And let's see if, as you know, master, market maker of all the data, I can imagine something going on between Paolo and Francesca. So I have access to all the data produced. I know that they exchange a lot of mails. Good. So I know that Francesca is following and retweeting constantly what Paolo produces on Twitter. Maybe we'll see later on, not about politics, but okay, most of the tweets she retweets. A lot of likes whenever he puts something on Facebook, because these guys are pretty old, so they are not on TikTok. You see this boomer stuff of that we're using like Facebook. Then they share the same interest. Let me play a little bit. I mean, so otherwise you get bored. So after yesterday, MLS, they share the same, they interest, they support the same thing. Then you go on political opinions, and then you see that, well, maybe the agreement is not that strong. So what happens? Okay, I got all the data. Maybe Paolo and Francesca, you know, they share something in common. Maybe they are more than friends. Okay, there are some sort of connections. Even if you are one retailer, even if you are Amazon, you can profile people. I mean, you know that myself, I bought this, and this, and another guy by chance bought the same things, the same series. So many users that, I mean, it's almost certain that there is another guy, or if not the same, very similar record of buyings. Then these other guys buys a new stuff. What Amazon does, he's profiling us and say, well, look, this guy, very similar to you, as much as I can tell from your records, has also bought these. Aren't you interested? Possibly I am. So they are suggesting to us the new buyings. On Netflix, they are suggesting to us what to see. Why? Because people who saw what we are seeing on Netflix maybe got interested in another series. So maybe also for us, this would be true. And they're pushing by profiling. You can do openly just to support and having an idea of what the crowd is interested in, selling stuff. You know, moving to news, it can be less agreement on the way in which you do that. No? So Cambridge Analytica, for example, was using methods based on the geometry of networks, based on profiling, to suggest part of electoral program of candidates to voters. And so we enter in a completely different area. We enter in the citizenship, the right to be informed by voters, what's true, what's false, and we're entering in the field why misinformation or information disorders start to be relevant, even if you're not a scientist. Okay, so let's proceed. Let's see what's going on. Of course, there is a lot of conspiracy theories going around, no? Because everybody's controlling us, scientists are controlling us. So allow me a little joke. No, I mean, so for example, this was circulating. So the point is that if you control everything, you know, you have the answer, and all the others, you know, don't know what's going on. It's not like that. I mean, nobody knows everything, of course, hopefully. And the more we know how these things work and how these things are related with each other, and the better defense we have, and the more we can contribute as a more healthy, information scenario and ecosystem. Of course, since the social aspects of that and the complex phenomenon that arises from the interaction of people, instantly this became very, very important, the study of fake news and misinformation. A lot of people in the US, but even people here in this side of the ocean, was starting studying fake news. No? So information that mimics the media, but not with the intent, of making you doing something that that is dangerous or put you in trouble. Then there are false information who instead is trying you to think something that is not real. There is misinformation in general that is with an idea on the back to drive you to do certain behavior. In general, we have various kinds of information disorders. So things that are not properly right. And of course, there are things that you cannot decide, like in mathematics. There are, sentences, we know about Gödel theorem now, in which you cannot say if it's true or not. But this, believe me, is a tiny fraction. Of course, they exist, but I'm in Rome now, it's not raining. That's true. Here where I am, there is no rain. It can be debunked easily that if somebody says it's raining now here. Okay, so there is a bunch of pieces of news in which, either it's true or it's false. There are, of course, statements for which you don't know because nobody knows, and statements for which nobody will ever know because they are formally not decidable. So that's the point. So let's restrict on the things in which we can do something. Point is that social networks, Twitter, Facebook, are important because a lot of people take news from there. In 2016, 50% of Americans used those platforms as the primary sources. 70% 1 year later said that at least some, if not the primary resources. So it's impressive. In Europe, not pretty different than that. So let's show after that what we did. Okay, so we studied networks to study the communication on Twitter. There is one social network on which we can take data freely with some restraint and limitations. And we built a network out of that. We discovered that this network has all the properties that it should before, and so must be handled with care. And let's see what we did. Okay, so the network we built, this is a network of retweets. Okay, so you go on Twitter, you download all the tweets in which people are talking about elections. We're talking about the last parliamentary elections in Italy, 2018. And we put the same color, two vertices. We'll enter into the detail of that, okay? Who share similar political ideas, either because they declared that, or because they are connected, and we'll see what does it mean, to somebody who has a political guy, political person, okay, can be female or male, Boschi or Renzi or Meloni or Pietro Grasso, okay. So I will use guy as a neutral term, okay. You can color them, and you can see that you see spots. And this is already important because it is mapping, is giving a metric to politics. So you can see blue, for example, is right-wing parties, red or colors red to red, the left-wing party. We have a convention that is the opposite to the one of the United States, where blue is the color of the Democrats and red of the Republicans. But I mean, I imagine you know what I'm talking about, being Europeans, so you can recognize. It's important, this metric, because you see this blue and this red, they are pretty similar each other in this metric. And as a matter of fact, they share some ideas together. The yellow are Movimento 5 Stelle. You see that scattered everywhere. So there is a bunch of persons with similar ideas, but also a bunch of persons, you know, that are more related to ideas of other parties. That's totally legitimate. I'm not doing any at all criticism or any comment on that. Okay, I'm just saying that this way of representing distances in terms of who's retweeting whom is giving to you information. Only that. Okay. And so what we did, because this is the detail, okay, I don't have a lot of time, but I would like to enter a little bit into the detail of the network who built that. We use the Twitter activity. We measure the polarization, so how strong you are in your ideas, but you also study the communities that you determine. And how's that? Okay. We essentially passed through another bipartite network. The bipartite network in which we have persons, people who produce tweets and people who retweet tweets produced by others, but more importantly, persons who put their political ideas up front because they are in a party, they are, you know, running for a place in the parliament, so you know which is their idea, which party they belong to. And other people, that could be software, could be bot, you don't know, who have not been marked with a stamp and say, okay, you are a real person, you are a validated user, while the others very often are validated users. Okay, so we have this bipartite network of validated and unvalidated, or people writing tweets and people retweeting. So how can I use this information to build my validated set of users, my spectroscopy of politics? Well, I have to use statistical physics for networks, finally. How? There is the possibility always that one network is there without any information, only by chance. You just happen to follow somebody, is happen to follow you, somebody else, you know, and then you build a set of connections, but you don't have a lot of interest in it. Okay, you can measure that. How? That will be back on this. Okay, this is the paper in which we do that, because every graph can be considered as the element of one ensemble. So a graph and its adjacency matrix, the matrix who reproduces that, is a set of 0 and 1, can be substituted by a probability. So if I give a probability to create a link between I and J, according to the value of this probability, I can have all the possible graphs. Okay, so far not very useful, but let's follow the steps of Gibbs. The event with the larger probability, so the class of graphs that are the most likely, I would say, to appear, well, you probably will observe those. We call that canonical ensemble, to be proper in what you're doing. So it's like saying, I have this distribution of the velocity, I don't care about the distribution, I just take the average value, and this is enough. Then I will do an error, but there are so many that, you know, this will be averaged out, and even if it's a large error, with respect to the average value, it will be tiny. So it works. So let's do like that. So this is what we did. And of course, the assumption that you take the most general means what? Maximize the entropy. Which kind of maximization we're doing? We're doing a maximization of the entropy given the constraint. Which constraint I have? Well, one constraint I always have is that the probability distribution of this graph must be normalized, and this is the one. But in many cases, I have another kind of constraint. So for example, I know the average degree. The degree, people know. So how many followers one politician has. Okay, this is the degree of the connection. How many retweets? This I can measure. So this is an observable. Whenever I have one of these observable, I have other constraints. So the correct way to proceed is to take all the possible Twitter graphs, just to understand what you're doing, and maximize the entropy, so this value here, but with this constraint. So I have to do, you know, these usual calculus stuff that we did when we do the derivatives, no? with the constraints. So imposing that this quantity is an extremal, so I'm maximizing this, so the derivative must be equal to 0, but with this coefficient that take into account the constraints that I'm putting into the game. So imagine I don't know anything, okay? So the only constraint I have is this one, the normalization. If I follow this formula, this requirement, so has to be maximized, means that P of G has this form. But here I don't know anything, so all these L lambda are 0. So I don't have this part. What do I have? I have only this part. Well, no constraint, only the normalization means that the probability distribution for the graphs with no constraints is for every graph this value, so it's constant, so it is a random graph. Okay, random graphs are those graphs that are all equally probable. Good. Typically, instead, we have the average degree. And when we have the average degree, well, I have the other parts. And if you do the mathematics of the other parts, then I can factorize the probability for every graph in a probability for every vertex, and the form that this probability takes has this shape. This has been demonstrated by Diego Carlaschelli and Mariella Loffredo in a physical review letter many years ago, but you will find here in these two papers all the references to that. So, okay, once you do that, we apply to the Twitter. So we have our Twitter data. There's a bipartite graph. We do this method, exponential random graph, we can also call the configuration model in this case. And you have to consider the bipartite configuration models. You do that, you compute the probability, and then you validate the network, in which sense all the networks that you produce with this trick, but for which the connections are too rare, below a certain threshold, probably they will never happen. Probably this is the noise. All the graphs for which the same connection stays there, and remember, we have more information here. So we have the degree, we have who's following whom. So we know, okay? We know a bit more than random graphs. So all the connection that remains, well, this connection probably are true connections, okay? You play this game once to associate unvalidated users to validate ones. So, for example, you want to know who is a bot and who's not. Sorry, I mean, that's for the joke. So you put on the upper layer the validated users, and you put on the lower layer the unvalidated users. You play this trick, and at the end, you know that these unvalidated users is reasonably connected with a validated one. So if you're talking about politics and this belongs to a certain party, well, this connection is telling to me that also this unvalidated user is connected or sympathizing with the same political party. This is the trick we used. Okay, so let's go to the result. You go on Twitter and you start downloading. Okay, we have to go back. Actually, this is what we did to build here, this network for the elections. Now communities, vertices can be colored, not only those who claim to be right-wing party, left-wing party, or journals, but also those who don't claim anything but are connected more than the average. Now, more than the average has a meaning to those. You color with the same, okay, with the same color. And then you can study those communities, and you can check the polarization, how strong is cohesive this community, and which is the strength with which they push their opinion. And then we made another analysis on the data set. On the data set, I'm about the 45 minutes, but I just need just a few minutes and I'm done. Another data set taken from the discussion on migrants in Italy. So people arriving in Italy, and the words that we're looking for on Twitter were immigrati, migranti, scafisti, ONG, Sea-Watch, barconi, clandestini, all the ones you see there. Okay, collected all of them, played this game of finding twice who's validated, who's not validated and associated to the validated, and then who's a real person, who's a bot. Okay, and so we have a certain statistical ideas, which is the audience of certain ideas, who is real and who is a bot. Again, we find, but this is obvious and this happens everywhere, that these networks are structured across communities. We find right-wing parties and government forming a single community. That's not strange, because at the time, this was when the right-wing party were in power in this legislature at the very beginning. The left-wing parties are split into two different communities. And we also found that half of the users interacts with uncertified users. Okay, so we'll probably start a discussion with somebody and you don't know if it's a real person or not. You don't know if he has the name who put on the Twitter, and so on and so forth. Okay, we published that on communication physics, which is to us the one of the phenomena was worth a little bit more of attention. First result is, okay, you can put a metric in ideas in politics. You can measure how distant apart two ideas are. I don't care which kind of ideas you have, but I can measure how far you are from this guy, how far you are from another guy. And so this can be done. But more importantly, you can see that most of the users are definitely bots. There are softwares you can use, Botometer. At the time, it was free for use. It's a software made by people in Indiana University. Now, I believe you have to pay something to use this software, but probably for academic purposes, you don't. Or you can contact the person, the colleagues, and explain the situation. I'm sure they happily do an exception. But you take these users and you check if they're bots or not. How? Well, for example, you sleep, we sleep. So we don't tweet 24 hours a day, every day in 1 year. If this happens, maybe it's a software, There are other things like that you can use to assess if this is a real people or not. But on average, you can say this is a bots. You check these bots, you check how they continue to go, which kind of news they retweet, and who's retweeting their news. And you find that one of the parties actually is using professionally these bots. Again, believe me, there is no whatsoever comment on ethicity of that. I don't care. This is an instrument. No? Some parts are using professionally, some other parts are using less professionally. So there is a bot squad in Italy. This bot squad, at the time of our analysis, was mostly connected with one of the communities and not with the others. But that's okay. I mean, it's legal. I mean, people can do that. Okay. But, I mean, this is what the data said. Okay, let's jump to the conclusion. Let me skip the echo chamber. I don't want to be too much long on that. Conclusion is that network theory, that is mathematics of complex systems, once used properly, because many networks deliver no information. They are simply the result of random connection, but you can filter out this noise if you use statistical physics methodology. Okay, validated users form a network on Twitter, and this network is structured in communities, and you can very clearly determine them. You can very clearly pinpoint in which part of this space you belong to. Unverified users can be put in this network, again, by using statistical physics, by checking how relevant are their connections in an ensemble of all possible different connections with the verified users. Bots can be recognized in the networks by their activity, daytime activity. For example, you can plot the network of those bots, and you can check that they are retweeting mostly the tweets of one of these sites. Again, this is important. So not all the community interact in the same way, this bot squad. And this, again, this way in which you can quantify, measure, and model this phenomena is brought to you by network theory. So networks are important in order to do that. If you don't know network theory, you cannot compute the probability properly. This is a disaster, and you find something that is inappropriate. So I would stop here. If you have questions, let me just give a bit of advertisement. I mean, we publish on networks a lot, as you can imagine, as a group, not only me, of course, tens of people. You can find all the information and paper at this web page. You can follow me on Twitter if you want. Maybe not. I mean, of course, it's up to you. You can write me if you have a question about that, and you can find me on the social network very clearly and very precisely. This is what we did. This is what other people did, and more interested in what we did. There is a new series, Cambridge Element, that is called The Structure and Dynamics of Complex Networks. You can see here the first volumes that have been published by, the best in the field worldwide. For a period, those little booklets are available freely, and they form, a series that will drive you through network theory very easily and, at the highest level possible, because communities are explained by Renaud Lambiot, because percolation is explained by Dorogotsev and Mendes, because higher order networks have been explained by Ginestra, Bianconi. So the expert in the field realized this series. Some are still free, some are not. If you're interested, I happily share of those. I'm editor of that. So now I'm really done, and thank you for your attention. And if you have questions, just let me know.
Thank you, Guido. Thank you for the nice talk. So I think there are a lot of questions from the audience.
Let's hope not.
Let's hope. So I can start maybe.
Please.
I have one actually. So it regards the degree distribution of bots. You've shown that the bots create a kind of sub-network inside the network.
Yeah.
Does it have a special degree distribution respect to the network of other people, of normal people, let's say?
Yes. Hopefully there were not many. We're talking about 100. So you don't have enough statistics to assess precisely which kind of statistics, if it's fat-tailed or not. And so we didn't consider like that. My intuition is that probably it's not a power law. It could be a fat-tail distribution, but essentially is very uniform. I mean, those bots, what connection between people is driven by a certain series of relations whose outcome generates a power law. And the origin of power laws is very debated. Here we deal with organized activity, so not the same rule apply. It makes sense that they're all connected with each other, and on average, more or less connected with each other. No? Some are more important, some are less, some are larger degree, and some are smaller degree. But if we had larger statistics, I wouldn't be surprised not to find a power law. That is pretty common, actually, in networks. But it's a very good question. Let me see if I can find a larger set of data, maybe with the guy in Indiana. Probably they already studied. So I will do my homework, let you know.
Thank you. So question from the audience. So it seems that we are very tired today, and so if not, I think we can thank Guido again.
My pleasure. Again, remember my email. Questions may arise later on. So yeah.
Ok.
La mia email.
Grazie mille per il seminario.
Grazie a
fatto
voi.
ancora l'italiano. Una domanda in conclusiva: possiamo pubblicare il seminario online?
Senza problemi.
Grazie.
Va bene, speriamo di incontrarci un giorno in qualche posto, una conferenza, per ritornare a quello che facevamo prima, però insomma...
Vediamo, stiamo ricominciando quest'estate, si ricomincia alla grande, mi sembra.
Perfetto. Va bene.
Grazie
allora,
ancora.
Grazie Guido,
a tutti.
complimenti.
Grazie per l'attenzione.
Ciao a tutti, buona serata.
Grazie.
Ciao,
Grazie.